uh, giving me an opportunity to speak here, even though I'm a last minute addition. So I think they found a substitute. So originally Surjeet was supposed to talk, and they looked for someone whose name rhymes the same. So they found Surjeet. So and the other thing is that I'm going to basically this talk is aimed at students. So I would like to ask the experts to excuse me for going into trivialities and spending too much time on trivial issues. And I should add that most of the things that I want to cover are already covered by Indroda. But this was an old presentation, and I didn't really plan it that well. So I'm going to talk about low dimensional systems. That's the saving grace. So I'll go more into cuprates, but even lower dimensions than high TC cuprates. So let's start. So before that, let me just since I said I'm talking to students. So when we look for magnetic systems, because that's what the idea is here. So magnetism is mainly confined in these parts of the periodic table. So this is the 3D series of elements, transition metal elements, where the 3D shell is successively occupied. And then you have magnetism coming from 4D elements such as molybdenum, ruthenium. Ruthenates are very, they are very commonly studied these days. And then you have magnetism coming from the 5D elements, particularly from iridium. And then, of course, there is this series of lanthanides where the 4F shell is progressively filled. And then you have actinides where the 5F shell is progressively filled. So what you need actually for magnetism is you need unpaired electrons. All right. So unless you have unpaired electrons, you cannot have a magnetism, because if you have all the electrons paired up, their spin degrees of freedom will cancel out, their orbital degrees of freedom will cancel out, and you won't get any magnetism. So, you may have seen this kind of thing earlier also, but do you know how many of these elements are actually magnetic? Magnetic in the sense that if I take a piece of titanium, would I be able to attract it to a magnet? If I take a piece of copper, will it be attracted to a magnet? These are the kind of questions that we are asking. Of course, I said copper, is often a source of magnetism, like in high TC cuprates, which Indra talked about. But if I take a piece of copper metal and bring it close to a magnet, will it be attracted to a magnet? So the point is that magnetism is sort of, it's a complex subject. So if you look at the periodic table, not all the elements are actually magnetic. In fact, there are very few elements that are magnetic. You can count them in your hands. So iron is magnetic, cobalt is ferromagnetic. Iron, cobalt, nickel, these are ferromagnetic metals, right? You're familiar with them, and they all three of them order ferromagnetically above room temperature. On the other hand, copper is not magnetic in the sense that it doesn't have a spontaneous magnetization, all right, and you cannot induce magnetization. Of course, you can. If you put it in a magnetic field, it'll get feebly demagnetized, right? So it exhibit diamagnetism, but it doesn't have magnetism of the sort that iron, cobalt, and nickel has. Similarly, from the lanthanide series, the 4F series that I showed you at the bottom of the periodic table, let's take the example of lanthanum. It has no unpaired electrons, and therefore it doesn't have magnetism. On the other hand, if you go from lanthanum to cerium, cerium has one F electron, and by virtue of that, cerium has a magnetic moment on it. All right, but whether if you put a cerium atom into a lattice structure, whether you will see an spontaneous ordering or not, that's another aspect that we will discuss. Now the thing is that even though iron is magnetic, but there are compounds of iron where iron doesn't have any magnetic moment, okay, and this is not an exception. There are hundreds of such examples where you have compounds of iron, cobalt, and nickel, where these elements do not manifest any magnetism, they do not have any magnetic moment on them. Okay. Then you have cases like zirconium, it is non-magnetic. You take a piece of zirconium and measure its magnetization, and you don't see any magnetic movement on zirconium or on zinc. But if you put them together and make a compound which is zirconium zinc 2, you have to take them in this stoichiometry. Okay, so you get a new material out of these two non-magnetic materials to start with, and this guy happens to be a ferromagnet. All right, and this ferromagnet is not the same as the ferromagnets that I have listed at the top, because the ferromagnets that I have listed at the top can be explained by quote unquote classical theory or the Stoner criterion, but this is a special ferromagnet which is called itinerant weak ferromagnetism. So, that emerges out of two apparently non-magnetic material. On the other hand, on this side you have copper, which is a piece of copper does not get attracted to a magnet because it is not a ferromagnet, it is also not an antiferromagnet, but there are compounds of copper which you saw in the previous presentation, where copper exhibits a magnetic moment. So, and then of course, from the 3D transition metal elements, you have manganese and chromium, which show this antiferromagnetic ordering. So, the point is that at this point in time, we understand most of these things, all right. Not everything, of course. For instance, we do not have a very proper understanding of how the magnetism emerge in this case, but most of the things we understand, at least if not accurately, but we have a good picture, good idea of why copper is non-magnetic and why it becomes magnetic here, and so on and so forth. Okay, and if I were to draw a map of magnetic or spin systems, so this is my own, and I mean this I have drawn out of my own thoughts, and I do not claim it to be exhaustive. All right. So, the way I look at spin systems is I will classify them as the local moment systems, and on the other extreme are the itinerant systems, and then you have something in between, which is the intermediate state between local movements and itinerant systems. So, in local movements, as the name suggests, the electron that is giving the unpaired electron that gives rise to the magnetic moment is localized at a lattice site, whereas in the itinerant case the situation is more complex. So, these materials often exhibit metallic behavior. In the local moment case, you have mostly the ground state is insulating, but then there are exceptions, and you can have local movement in metallic rare earth compounds. For instance, here where the rare earth movement is highly localized, and there is a reason to that, because the 4F shell is pulled towards the nucleus, and it is well shielded by 5p and 6s, I believe, not 6s, but 5p and 5d most likely electrons, and therefore they retain their local movement. And then you can also have local movements in situations like this. So, for instance, you take gold is non-magnetic, but you can put a tiny bit of iron in there. Okay, impurities, iron as an impurity. So, when iron goes into a gold matrix, it retains its magnetic moment, which is not always the case actually. Okay, so this was basically described by Anderson impurity model, whether impurity will retain its magnetic moment in a host metallic matrix or not. And in this situation, you see a many-body effect, which is known as Kondo effect, which leads to an upturn in the resistivity at low temperatures, which means that the resistivity of the material increases upon cooling rather than decreasing or becoming a constant. And if you increase the concentration of impurities in the host matrix, then you get into what is known as the spin glass state, where this impurity at the magnetic moment on these impurity atoms, they start interacting with each other. So, you can see that parts of this map are connected. For instance, from Kondo effect you can come to Kondo lattices in rare earth materials and heavy fermions. So, in order to even get familiar with the terms that are used here, for instance, Mott insulator, the effect of dimensionality, both the lattice dimensionality as well as the spin dimensionality, and the kind of ground states that you get, for instance, spin liquids and spin ices and spin glasses. You need to devote at least one module in an advanced condensed matter physics course just to get familiar with these terms, just to get start talking with people who are working in these areas, and understanding them of course will require much more time. And then, as I was telling you, that between the itinerant picture where the electrons that gives rise to spontaneous magnetization, a part of those electrons is also contributing to the electrical conductivity. So it's a very sort of flux like situation where, for instance, the d electrons of iron would be partially localized at the iron site. And then in between these two, if you look at 4D, 5D transition metal oxides, there you get a situation which is akin to the situation that you come across in 3D transition metal oxides, which is the Mott insulator. But here the Mott insulating ground state is driven by the spin orbit coupling, all right, not the usual on-site Coulomb repulsion. So this was a very broad map of how the magnetic systems can be classified. And in this particular presentation, I am going to look at this part, which was covered quite extensively in the previous presentation. So, what I am going to show you will probably reinforce the concepts that were introduced in the previous presentation. So, this is what you saw previously. So, this is a compound lanthanum 2 copper oxygen 4. This is the parent compound of all the high temperature superconductors, and what the structure of lanthanum copper cuprate looks like is shown over here. So, what is important for us is to see that these copper ions, which are depicted here with the black balls. So, these copper ions actually form a square lattice. You can see that square lattice over here, and between any two copper ions there is an oxygen, okay, and this copper oxygen octahedra which you see over here, it is slightly stretched along the z axis, okay. So, if we look at the chemistry of this, so lanthanum has this as the electronic configuration, so xenon like electronic configuration, and then you have one d electron and two s electrons. Copper has this as its electronic configuration. So, basically lanthanum and copper can attain the inert gas configuration by giving away 3 electrons, and in this case for copper, if it gives away its 4s, it gives away 2 electrons, then it will remain with 3d9, but by giving away 2 electrons, oxygen will satisfy its requirement for the inert gas configuration. So, basically what happens in this compound is that lanthanum has the 3 plus oxidation state, copper has 2 plus because it gives away 2 of its electrons, and therefore, it remains with 3d9 configuration, okay. And 3d9 is basically a one unpaired electron because d shell can take 10 electrons. So, you say that copper has a spin half, but of course, these d orbitals which are energetically degenerate when they are in vacuum are no more have the same energy because they are seeing these negative charges around them. So, depending on the orientation of the lobes of the d orbitals, there is a splitting of these 5 d orbitals. So, z square and x square minus y square orbitals, they are directly seeing the oxygen ions. So, in this case, for instance, the x in the xy plane, and for the z square case along the z axis, and because of that, so if the electron has to reside on the z square orbital, it has to face more repulsion from the oxygen sitting here compared to the situations depicted over here, because in this case the orbital, the lobes of the d orbitals are pointing in between the oxygen ions. So, therefore, the repulsion is less compared to the repulsion in these cases. So, compared to the free ion, by free I mean the D9 in vacuum, when you put D9 in an octahedral coordination, then the energy of x square minus y square and z square will go up, and that of these three orbitals will come down compared to the energy in vacuum, all right. And this set of these two together are called Eg orbitals, and these three together are called T2g orbitals. And now since we have 9 d electrons, so T2g will be completely filled. So, this forms the core, and your Eg has 3 electrons, which is 1 less than the completely filled. So, therefore, it has one spin of 1/2, all right. Now, if we go by this picture as was explained in the previous presentation, then you have this dz square orbital which is completely filled, all right, and you have this dx square minus y square orbital which is 1/2 filled, okay. And sorry, before that I should tell you why z square orbital is completely filled and not x square minus y square, though Indra also talked about it in his presentation. So, here as I was telling you, there's a stretching of the octahedra. This is known as Jahn-Teller distortion, and this distortion is happening because the system can lower its energy. So, the orbital degeneracy is lifted. So, 2 of the electrons have lowered their energy, and the energy of one of the electrons has increased. So, overall there is a net gain in the energy, because the total energy has decreased, since 2 of the electrons are lowering their energy compared to 1 electron which is raising its energy. So, there is a net gain in the electronic energy, and if this gain in electronic energy is if it overwhelms the energy cost that you would pay in distorting the octahedra, then the octahedra would like to distort itself, and that's what happened. That is what happens here in this case. So, therefore, you remain with 1 unpaired electron in the x square minus y square orbital, and that is what is depicted over here. So, if you do the band theory, you have 1/2 filled band, and therefore, this material should have been metallic. But actually in reality, if you measure its electrical conductivity, you would see, or rather resistivity, if you measure the electrical resistivity, then it does not behave at all like a metal, but rather behaves like a good insulator, because the electrical resistivity is very high, all right, and also it increases with decrease in temperature. Okay. So, this is one thing that we have not we cannot understand just on the basis of band theory without introducing electronic interactions, as was explained in the previous talk. So, let me quickly go through this. So, this is the tight binding term. Okay. If so, this allows electron to hop from one side to another side, and this is the hopping element, matrix element for the hopping term, and you have added this Coulomb on-site repulsion. So, if 2 electrons sit at the same site, which by Pauli's exclusion principle is allowed, because each orbital can take 2 electrons of the opposite spin. But because of the strong U, which does not let 2 electrons sit on the same site even if they have oppositely directed spin. So, because of this strong U, your electrons are basically confined or remain, they will remain at their respective sites. They are not allowed to hop, all right, from one side to. So, therefore, the material will behave like an insulator and not like a metal, because for it to behave like a metal, the electron should be able to hop from one side to the other side, and that will happen when U is 0. If you make U 0, then of course you have a half filled band, but if U is non-zero, then there is a competition between the T term and the U term. The U term is trying to keep the electron at its respective side. It is preventing the electron from hopping from one side to the next other side. So, this is depicted here in this form. So, basically you have this d orbital x square minus y square will split into this two bands. This is known as lower Hubbard band and this one is the upper Hubbard band, and the lower Hubbard band is completely filled because this dx square minus y square can take 2 electrons per site, and now you have 1 electron per site here, and this is the second half of it, and these are separated by the energy U, and it was very nicely explained in the previous slide that the competition between U and previous talk, that the competition between U and T can give rise to a metal to insulator transition. And also what is very important for this presentation is that if U is very high, then this Hamiltonian can be shown to map onto a spin only Hamiltonian. Okay, so that can be shown, and the Hamiltonian then is called the Heisenberg Hamiltonian, which is simply H equals J times SI dot Sj, where J can be written down in terms of the parameters U and T. So J is essentially T square by U, okay, as was explained in the previous talk. So basically you move, so what you see here, what happened here is that the charge degrees of freedom are frozen out, all right, they are gapped, the charge degrees of freedom are gapped, okay, and the spin degrees of freedom are the degrees of freedom that remains, all right. So what do the spins do? So this is the question that we are trying to answer. So yeah. Okay, good. So now we are remained with only the spin degrees of freedom. So I can actually replace this Hamiltonian by the one which you would probably know by now. Let me nevertheless write it down. So basically is this H equals J Ij, where I and J are the site indices, and then you have Si dot Sj, where I and Si and Sj are the spin halves, and you then sum it over all the sites. So this is basically the Hamiltonian, and what is depicted here is that the x square minus y square orbital has only one electron. That electron is allowed to delocalize only over these nearest neighbor bonds. Okay, so this is known as virtual hopping. Okay, so what's happening is that the electron, by virtue of this T term, which is not exactly 0, there is some T non-zero T term is the transition matrix element is there, and because of that the electron once in a while hops onto the copper and comes back, This is known as virtual hopping. So there is no global hopping. It's not that the electron can just go on and on and on and on. It's just limited to the nearest neighbors. So the electron will go here, and if it does that, so what I am trying to prove here is that for such a system the ground state would be antiferromagnetic, and to prove that I first assume that the ground state, let's assume that the ground state or the spins at each of these sites is ferromagnetically ordered. So this copper spin is pointing up and this one is also pointing up. Oxygen has two electrons, and then in the p orbital, okay. So this can go here, okay, and after that, once this electron has moved here, after that you cannot have hopping of this electron either from here to here or hopping of this copper electron from here to here. This is not allowed, and of course this is not allowed because you cannot have more than 2 electrons per site. So therefore here the excited state is not as low in energy as in the case of antiferromagnetic alignment. Why? Because in this case, if the oxygen hops if the electron hops from here to copper, okay, like this, then this hopping channel is still okay. It is still open. So therefore the system can lower its energy. So basically what's happening is that this localized hopping back and forth, it's bringing the energy down. All right, this is called the virtual hopping, and this mechanism is known as super exchange mechanism, and this gives rise to an antiferromagnetic ground state. So what we have learned then is that La2CuO4 is not only an insulator, but it also orders magnetically, okay, below a certain temperature. There is a spontaneous ordering, and this temperature is known as the Néel temperature. All right. So, this is an antiferromagnetic Mott insulator. Now, here is another example of emergent phenomenon which you saw in the previous slide also. So, previous presentation also, I am keep saying slide, excuse me for that. So, in the La2CuO4 case, the situation is that every site has just one electron. So, this is the case of half filling, because you have each site, each orbital can take 2 electrons, but there is only one. So, this is a half filling case. So, in the half filling case, you have an insulating ground state, but if you dope it with holes, which means that at some of the sites you would make the orbital completely empty, and then the electron can hop onto that empty site. And if you do that, then you induce metallic behavior into the system. The magnetic ordering, which was because of super exchange or the virtual hopping, starts decreasing, and you start seeing a very interesting phase, which is superconductivity at low temperatures. And besides the superconducting phase, you also see a plethora of emerging phases in these kind of systems. So, this was just an example to motivate you to that the emergent physics happens in these materials. So, let me now go to from 1D, from 2D, let me go to 1D. So, if I replace lanthanum, which is tri-positive, as I mentioned to you a few slides back, if I replace it with strontium, which is divalent, then what will change here? Because the formula unit has to be charge neutral. So, if I replace lanthanum by strontium, then what is going to happen is that you have now strontium. So, it is +4, because you have strontium 2, and strontium is carrying 2 positive charge on it. So, it is +4. Copper is again 2 positive. So, this is +2. So, oxygen, which was 4 in this case, in this formula, should reduce to 3. So, now you have 1 less electron per formula unit compared to La2CuO4. Is this clear to everyone? Because in order to make the charge, if formula unit charge neutral, I need to remove 1 oxygen. So, if I replace lanthanum by strontium, I should remove 1 oxygen from the formula unit, and that affects the structure in a very interesting way. So, the oxygen from the XY plane or the AB plane of the crystal structure. So, you see the oxygen sitting here. This oxygen is no more there in the strontium case. So, this oxygen is gone from here. Okay. So, now the coppers can interact with their nearest neighbor only along this crystallographic direction. Why? Because along this direction the super exchange path is removed. Do you see that? The super exchange path has been removed in this case, because there is no oxygen in between. All right. The other change that you should notice, besides the change that I just mentioned, the other change you should notice is that now copper is in a square planar coordination, right, because the apical oxygen is gone, completely gone. Okay. So, these are the two changes that have taken place when I replaced lanthanum by strontium, and by this example I am also trying to motivate you to think that chemistry and physics in the condensed matter systems is kind of, they are strongly linked to each other. So, you can, in order to manipulate the properties of materials, you should know a bit of chemistry, otherwise it is not possible to do that. So, here what you have then is a situation where the copper spins can only interact along this axis of the crystal, and therefore, you have reduced the structure from a square net to one dimensional chains. All right. So, this is what you have now, you have a 1D chain. Now, in the 1D chain, like for instance this one, I said that there is no interaction between these two coppers, but is it really true? Is it really true? Okay, yes, you have removed the oxygen, the intervening oxygen. So, super exchange is gone, right, but they can still have a very feeble dipolar interaction between them. Besides that, this copper can interact with this copper. The exchange path is quite long. For instance, the exchange path in this case is via this oxygen and then this strontium and then this oxygen and then this copper. A longish exchange path, but the exchange path is there. So, therefore, the copper spins are interacting primarily along this direction. That is true. That is the in-chain interaction. But besides that, there is also an interchain interaction. The interaction which exists between the copper spins in this chain and the copper spins, for instance, in this chain. I mean, if I complete this unit cell, you would see a chain forming here as well. All right. So, this interaction, which is interchain interaction, is called J prime, okay, and the interaction that exists within the chain is called intrachain interaction, and I will depict it throughout this talk by J. Okay. So, how good the one dimensionality of your system is determined by the ratio J prime by J. If J prime is 0, then of course your chains are completely isolated, all right, and then you have a very good one dimensionality. On the other hand, if J prime is J, you have recovered the 3-dimensional case. You see that? So, depending on the ratio J prime by J, because in real systems there is no ideal one dimensional system, there is always a non-zero J prime. Okay. The question is, how small is this ratio J prime by J? And in the case of strontium 2 copper oxygen 3, it so turned out that this ratio J prime by J is of the order of 10 to the power minus 3 or minus 4. So, 3-4 orders of magnitude difference between the two J's. So, therefore, this compound is a very good representative of 1D systems. Is this clear? Up to now everything is fine? All right. So, if you want to study the physics of one-dimensional chains, then you have to find systems which are in this region of this one-dimensional phase diagram that I have drawn here. Okay. So, now the question comes, why should one be interested in studying one-dimensional spin systems? So, you see, the thing is that in 3D, when there are when in case of 3-dimensional or 2-dimensional materials, the electrons or fermions are, if they are interacting with each other, you can take care of these interactions using the Fermi liquid theory, which is the cornerstone of understanding of the metallic system. So, for instance, if today you understand how copper behaves or why iron is ferromagnetic because of the Fermi liquid theory, all right. But of course, in 3D also there is a class of systems known as strongly correlated electron systems, and within that class of materials there is a subclass where Fermi liquid theory breaks down indeed. Okay. So, even in 3D the Fermi liquid theory breaks down, but in 1D, even for the tiniest of the interaction between the fermions, whether the fermions are spin or the electrons, the Fermi liquid theory breaks down. It does not work. All right. So, this is the important point. So, if you want to look at it in this analogy, if you are in 1D world, okay, you cannot bypass or you cannot go from here to here unless you fly, of course, but if you are flying, you are already using the second dimension, right. So, in one dimension, and this situation will come very soon in maybe half an hour when you will stand for the lunch in a queue, you cannot go first, bypass the people who are standing in front of you. On the other hand, if you have more than one dimensions, like here in this case, you have this degree of freedom as well, you can dodge and go past the others. Okay. So, in 1D the interactions are very important. That is the message that I would like to give you, and the Fermi liquid theory breaks down. So, we need to work with another theory that does not work, that does not a new theory that is not valid for a new theory that is valid for the 1D systems. The other thing which I should mention is that in 1D, the kind of physics that you get, that you see, is very different from what you would see in normal three-dimensional spin systems. And I am going to give you one or two examples of such cases, all right. So let's go further, and now we are really into the main talk. So this is what I plan to do. What I will do is I'll give some basic preliminary things about, tell you about the spin half Heisenberg chain. Why Heisenberg chain? You remember, in fact, Indra also talked about Heisenberg model in his presentation, that you can, your Hubbard model boils down to the Heisenberg model in the limit of strong U. So this is what we are going to do. When we say, important distinction, when we say Heisenberg spins, which means that the spins having all three components, Sx, Sy and Sz. When we say Ising spins, that means the spins having only one component, either up or down. So let's say Z. So you will have Sz, which is up or down. Okay. So we will be talking most of the times, we will be working most of the times rather with the Heisenberg spins, and we would be working most of the times with spin halves. And the reason why we will work with spin halves and not with spin 3 halves or 5 halves or 7 halves would become clear in fact, because I haven't yet explained it in a minute from now. And then what we are going to do is we will introduce impurities in these chains. And now, as I told you, that in a chain it is impossible to go around, you cannot dodge, there is no space for dodging. So therefore, if you introduce impurities, even the very, very tiny amount, quantity or amount of impurity can actually affect can completely, qualitatively change the ground state of your system, and this is what I am going to show you. Okay. So let's get going. Before that, okay, this is also important. So in order to do all this, which I showed you in the previous slide, you need very nice crystals of these materials. Why crystals? Why not a powder sample? Well, you know that the chains are aligned along a certain crystallographic directions. Okay. If you work with a powder sample also has crystallites, but these crystallites are micron in size, micrometer in size, all right. So what happens is that the chains are randomly oriented, all right, because from one crystallite to the other crystallite, the orientation changes because these crystallites are randomly packed into your polycrystalline material. So you need a single crystal in order to study these materials. So here is an example of a single crystal of strontium 2 copper oxygen 3, all right, which is a spin half chain, 1/2 chain. And the facet that you see here, I mean, I don't know if you can see the reflection of the graph paper on this. So these are naturally cleaved surfaces. So you grow a crystal, okay, and then because along this is actually perpendicular to the AB plane of the, this is this direction. So along this direction, the bondings are relatively weaker, and therefore it tends to cleave. These are images that you would have seen yesterday in Luminissa's talk, which basically deals with how we characterize, how we know whether the crystal that we have grown is good or not. Okay. So I give you example of one of the characterization techniques. This is known as rocking curve. So what are we doing here? So we have a large crystal, let's say the size of, let's say about a few centimeter long and a few millimeter in diameter, and we want to see whether this crystal is a good crystal or not. So what we do is we place it in the path of an incoming neutron beam. Okay, this is a monochromatic neutron beam. So you know, if you are if in the passage of this neutron beam there is a crystalline material, then the neutron beam will get diffracted, Bragg diffracted along different direction, Bragg direction. So you put your crystal in such a position. This is your source. You put your detector over here, such that your detector is actually detecting a Bragg reflection from the crystal. All right. So what that means is that if you move your detector too much here or too much here, then you wouldn't see this reflection, because the Bragg reflections happen only along particular directions that satisfy the Bragg's law, right? Now, after fixing the detector, what you do is you rock your crystal a little bit around the Bragg position, okay? Around the Bragg position, you rock it a little bit, and if the crystal is a good crystal, then you should immediately see an extinction, isn't it so? And if the crystal is not bad, if it has inhomogeneities, okay, and if it has lattice defects, then you would see a broadening of this. Okay, there's always some broadening which comes from the instrument, that is called instrumental broadening. Okay, so if you take away the instrumental broadening, then whatever broadening remains defines the quality of your crystal. If the crystal is very good, then once the instrumental broadening is removed, then you should not actually have any broadening. It should be a delta function ideally, okay? But there's, of course, you know that there's no material which is perfect, where the lattice is perfect. There are always lattice defects. There are, you know, ions that exchange positions and so on. So basically this analysis gives you and tells you about the quality of your material in a much greater detail than any other technique. For instance, if you use X-rays, they cannot penetrate into the bulk of the material, but the neutrons can. Why? Because they are electrically neutral. They only have a spin, so they interact only with the spin degrees of freedom. And if your material is not magnetically ordered, then of course it doesn't matter. It doesn't matter that much. All right. So this is an example of how the materials are characterized. Now, if I were to tell you how these materials are grown, because you see this is a pretty large and nice crystal. So how do we grow them? So in order to grow them, we use a technique which is known as a floating zone technique. So we use a furnace which is known as image furnace. Why image furnace? Image furnace because we have sources placed here, but all the action. Okay, let me go slowly. So basically, the furnace consists of these reflectors. So these are perfect, very nice reflectors. These are made of quartz, and they are pretty well ventilated, and the inner surface is coated with silver. So you have a reflector sitting here. So because the cross section is elliptical, if you put a source at one of its foci, then after reflection, the light converges at the second focal point. This is the property of an ellipse, which comes from the Fermat's theorem, that if you put the distance from one foci to the perimeter to the second foci is a constant, right? So this, if this is S1 and this is S2 and this point is P, this is how you define an ellipse, right? So SP1, S1P plus PS2 is a constant. So this is the light. This is the path that the light follows, no matter where it hits the reflector. If it hits the reflector here, it will go here again. It hit the reflector here, it will go here again. So basically, what you're doing is converging all the light that is emanating from this lamp into this very small volume. Okay, the size of this volume will, of course, will be determined by the size of the filament that you're using here. If you use a point source, you get a point over here. But of course, you cannot have a point like filament, right? So filament has a certain size, and in fact, you need a certain size because you would want the heat flux to converge over a small volume, not too big, not too small, just the size of the this crystal that you are trying to grow. So what you do is you take your material, which is to be grown as a crystal. Okay, you cast it in the form of a rod. Okay, how that is done is not very important, but it's not very difficult. You can cast it in the form of a rod, and then you take two such rods, and one is fixed to the lower end of the furnace, and the other one to the upper, and you bring them, and these two can be moved. So you bring their free ends into this hot zone. Okay, so there you melt, and this is the kind of melt that you get, and then what you do is you move both of them down simultaneously at a very slow speed, and what that does is that transforms this dull looking part into this shiny looking part, which is the crystal. So which is what you see here. So this is the rod, which is just a compacted powder, and this is actually the crystal which is coming out of this compacted powder when you run this process over many days. All right, so I have a picture of it. I hope it will work. Yeah, it's working. So you see, the upper and the lower shafts are also turning, and the reason why they should turn is because you want this melt to be homogeneous, and also the reflectors are actually, there are only 4 reflectors, so you want the temperature distribution to be uniform in the xy plane, if you call this as the z axis, and this is the xy plane. Can I take your question in a minute? Okay. Well, these are other details because the cuprates that I am talking about are a little more, I mean, there's more subtlety in growing those crystals, but I think I will probably not go into that because that will eat up a lot of time. So let me skip that part, except for mentioning that when you're growing this material, strontium 2 copper oxygen 3, this melt has a composition which differs considerably from the composition of the material which you have taken at the top, or the composition of the material of your crystal, which is Sr2CuO3. So basically what you have here is a flux. It's a material in which your parent material gets dissolved and get exsolved at the lower interface. So at the lower interface you are exsolving the material, at the upper interface you are dissolving the material. So it's a very interesting, this is a dynamical equilibrium that sets in, and because of which you get these nice crystals. And it's not, I mean, you can get, so this is the situation when the material melts congruently. In this case, the melt has the same composition as that of the compactified rod or the crystal that you are growing. So things are fine, alpha and alpha. But then it changes to dramatically. Here you have alpha, and then the composition, alpha is the composition, and then gamma is the composition of the melt, and then you again get a crystal which has a composition alpha. So this is called non-congruently melting behavior. Okay. So well, let's look at now the chains. So in the spin chains, there is no long range ordering, which was mentioned in the previous talk also. In fact, Heisenberg spins in dimensions 2 or less do not order magnetically. All right. So in order to argue that, you can use this free energy argument. So here I have taken the spin to be a classical spin. It's just an arrow. Okay. It's need not be a spin 1/2. It can. I mean, I have left the spin size to arbitrary. So you write the free energy as U minus Ts, and and this is a chain, this is an endless chain basically to induce periodic boundary conditions, and I assume that the system is antiferromagnetically ordered. So you have this up down arrangement, and if you disrupt this arrangement by by turning one of the spins, let's say at the jth site, so you will basically make these two bonds unhappy, and the consequence of this is that your U, that is the energy, the magnetic energy, will increase, but at the same time the entropy of your system will decrease considerably, because you could have flipped this spin at any one of these sites. All right. So the entropy would scale with the length of the chain. Do you see that? Because you can flip the spin at any one of these sites, whereas your U is a fixed number because you have only broken two bonds independent, you have only made two bonds unhappy independent of where you flip the spin. So you can flip it anywhere. So this tells you that the free, so if for a large long enough chain, this entropy term will win over this U, and therefore your free energy will be less than 0, and hence no long range ordering situation will be more preferred compared to a long range ordered state. All right. So is this argument clear to you? I assume that let there be long range ordering, and then I proved myself wrong by giving this free energy argument. But what happens at t equal to 0, and especially when the chains are spin, when the spin is 1/2. So when the spin is 1/2, you write this your Hamiltonian J S1 Si Sj, and then you can write it in terms of ladder operators. Okay, and then you can show that if you construct an eigenstate where all the spins are pointing in the same direction, and if you act with this Hamiltonian on this eigenstate, you will see that this eigenstate, this state that you have prepared, then you would see that this actually is an eigenstate of the your Hamiltonian. So that means this is the true ground state. So for a spin 1/2, up is very much allowed, and this is the energy. On the other hand, if you look at the excitation, so if you flip spin at one of the sites, let us say the jth site, okay, then you would see that this is actually, this is not a eigenstate of this Hamiltonian. So which means that if you act with H on this, you wouldn't get this back. But however, if you prepare a linear superposition of this, which is written over here, a linear superposition is actually happens to be an eigenstate of, not an eigenstate but eigenfunction of this Hamiltonian, and this basically is a way to say that your system will have a ground state where all the spins at t equal to 0, where all the spins are pointing up, and then at any finite temperature you will have these spin waves induced in your system. So this is the usual spin waves that you would see in a 3-dimensional magnet. But if you go to an antiferromagnetic case, you would see, if you prepare a state where the spins are up, down, up, down, up, down, then you would see that this is not even an eigenstate. And the reason for that is, if you write it in terms of ladder operators, then this term in your Hamiltonian, which is known as the transverse terms, so it basically flips the spins, all right, and because of that spin flips, you don't actually get an antiferromagnetic ordering even at t equal to 0 in a spin 1/2 chain. So this, I hope this distinction is clear to you. In a ferromagnetic case at 0 temperature you get all spins up, but in antiferromagnetic case you don't get up, down, up, down, up, down. Why? Because this transverse term tends to disrupt this ordering. And then you may ask this question, then what is the ground state of an antiferromagnetic spin 1/2 chain? If it is not up, down, up, down, up, down, then what it is? And the answer to this is that there will be spontaneous spin flips. So for instance, this is a section of the chain. So there will be a spontaneous spin flip, and that will, so once this flip has occurred, it will create these two domain wall like excitations. Okay, so each one is carrying a spin 1/2. How do we know that? Because in this section has a net spin 0, but this same section, when you have flipped one of the spins, has a spin 1. So therefore the net change of spin is 1, and this is shared by these two domain wall like excitations. Why domain wall like? Because these excitations now can propagate along the length of the chain without any additional spin flips, which means that without costing any additional energy. So therefore you have these domain wall like excitations. So these are called spin-ons. So in an antiferromagnetic chain, if you have to think about its ground state, then the ground state is quasi long range ordered, which means that you have long regions where there is antiferromagnetic ordering, but then suddenly there will be a spin flip, not because of temperature but because of quantum fluctuations, and that is where I am trying to come to, that why I mean, in what ways this is different from, or this is quantum in the sense that the previous case is not. So that so this spin flip, and that will divide the chain, this segment, in two regions, and then these domain walls can actually propagate along the length of the chain. If your spin is 5/2, let's say, okay, then what your transverse operators would do? The transverse operator would make 5/2 to 3/2 or to 1/2. But in the case of spin 1/2, once the transverse operator works on the spin 1/2, it goes from +1/2 to -1/2. Okay, so it's as disruptive as this, and that is what it means by quantum fluctuations or very strong quantum effects in a spin 1/2 chain, and not the higher spin 1/2 chains. So yeah, I mean these excitations are fermionic, okay, and so the charge degrees of freedom are frozen. The charge is not flowing along the length of the chain, but these kinks are flowing along the length of the chain. So but each of these is carrying a spin 1/2. So you say that you have a fermion, which is a chargeless fermion, spin 1/2, which lives in this one-dimensional world, and of course they interact with each other because they cannot go past each other without really scattering against each other. So therefore you are dealing with a interacting one dimensional system, fermionic system, and to describe this, the framework that you need is known as Tomonaga-Luttinger liquid. All right. So I don't know, I mean this is actually how much time I have? 5 more minutes. Okay. So Tomonaga-Luttinger liquid, if you have to experimentally verify this, if you have to really see what it is and if it really exists or not. So let me tell you that the theoretical predictions for what the spin excitations would look like. You remember in the ferromagnetic case, the excitations were spin waves, right? And the spin, in the case of spin waves, the dispersion, which is basically energy versus momentum, okay, energy versus momentum, are single valued functions, all right, like you have for phonons. For instance, you have acoustic waves, you have optical phonons and acoustic phonons. So similarly for the spin wave, but in this case you have a very crazy situation, because when you create a spinon, okay, these two spinons are created by one spin flip, and these two spinons can share the momentum of the neutron. Okay, let me tell it more clearly. So what we are trying to do is we are trying to measure the excitations in this case, which is done using inelastic neutron scattering. So what happens is that a neutron comes in, okay, talks with the chain, with the spins in the chain, and then goes out. Okay, so when it goes out with a lesser energy than it has come in with. That is why it is known as inelastic neutron scattering, and the energy that it has lost to the system is actually the energy that the system has gained. Okay, so by calculating the energy difference between the incoming and the outgoing neutrons energy, you would know how much energy has been given to the system. Okay, so that is the y-axis of your excitation spectrum, and by measuring the change in momentum, because you are sitting with a detector and you know where the source of neutron is located. So you know the k vector of the incoming neutron, and you know the k prime of the outgoing neutron, and the difference of these two would give you the momentum which is lost into the system. So by conservation of momentum, that k vector minus k prime vector is actually the momentum that your system has gained. Now in this case, since you are in one go, in one flip, you are exciting two fermions, not one. You remember these spinons appear always in pair. So you are exciting two. So since you are exciting two, they can share momentum arbitrarily, or for a given momentum transfer, they can share energy between them arbitrarily. Okay, what that means is that all the energy can be taken by one of the spinons, and the other may not take any, or they may divide it equally between them. So what that means is that you get a continuum of states instead of a. So here you see that you have this continuum which has a lower bound as well as the upper bound, and this continuum in the inelastic neutron scattering is one of the hallmarks of a spin liquid. So if you have to see whether a material is actually a spin liquid or not, you would do inelastic neutron scattering, and you would see if you see any continuum in the inelastic neutron scattering spectrum that you are measuring. And in this case, by default, you see that, and this is known as two spinon continuum. All right. So this is the experimental data, and this is the theoretical calculation using Bethe ansatz. And this has been shown now on a number of one-dimensional systems. Okay. So I will probably stop after this slide. This is my final slide, even though I had a lot more to cover, but I probably should have used my time more intelligently by not spending too much time on the Hubbard model and so on cuprates. But anyways, I hope you liked it. So this is my final example. So for a pristine chain, I showed you in the previous slide, this is how the calculated excitation spectrum would look like, and I am showing this again in the next slide, but I am showing only one half of, I am showing only not from -1 to 0, -1 to to plus, 0, yeah. Instead in a different region, minus 0.5 to plus 5. So you see this. What I mean is that if you take this and paste it here, then you would see the 2 spin-on continuum. So it's shown a different region. So we are experiment. So this is actually the experimental result, and its last slide I'm trying to explain to you what is going on. I mean, how interesting experiments one can do with the spin chains. So for a spin chain, which is where the translational invariance is not lost anywhere at any site of the at any of the lattice, which means that you have a nice 1/2 spin chain, you expect to measure this, all right. But if you prepare a chain where you replace the copper by an ion which has no magnetic moment on it. So copper has spin 1/2. You can replace it with zinc. Zinc is 3d10. There are no unpaired electrons. So zinc is scalar in that sense. You can replace it with nickel. Nickel 2 plus. Nickel 2 plus is d8. In its low spin state, there are no unpaired electrons. So nickel has 2 spin states, low spin and high spin. And apparently in this system, the nickel has the low spin state. So you can replace it with nickel. And then you create a point in the lattice where the translational invariance is locally broken, right? Because this invariance that was there previously is locally broken here. Now, if you're doping your chain with a very small amount of impurities, what you would get, you will get a finite lengths, chain lengths, where the chain looks like the pristine chain, and then you have this point, and then you have the next segment, and so on and so forth. Okay, so you would induce, or the spin-ons would be created in these regions, in this section of the chain. But the spin-ons are actually confined between these two boundaries. So this will act like a boundary. Why? Because as I told you, the translational invariance is lost here. So therefore you have these two boundaries, and the spin-ons are actually confined within these two boundaries. So this is very similar to a situation that you would encounter in +1 introductory quantum mechanics course, where you have V equal to 0, which is the box is akin to this region, and then you have these boundaries which are analogous to these points where the chain is broken. Okay, so what you now expect to see, so the spectrum which was continuous, so there was a continuum of states, we call it a gapless spectrum, because you can excite these excitations, the spin-ons gets excited even at the slightest of provocation. So now what you see is a gap. That gap has opened up, and that gap is actually a consequence of these scalar impurities. To verify that what you have hypothesized is correct, you can change the impurity concentration. So for instance, from 0.1%, you can make it 0.25%, maybe 1%. By doing that, you are changing the length of the box. When you change the length of the box, what happens to the gap between the ground state and the excited state? So as you squeeze the box, the energy gap increases, and you see that in your experiments. So I think I'll not go into these things, and I will stop here because it's already 1:15. I'm sorry. Okay. Yeah, sorry, you had a question.
So, regarding your X-ray point about observing the structure, as you mentioned, like it cannot go. I mean, we cannot get more detailed resolution of it, and you were mentioning about using neutrons. So, are you talking about the neutron microscope?
Neutron spectroscopy. So, yeah, I mean, there's a source of neutrons.
Yeah.
which is typically a nuclear reactor,
Yeah.
and you get neutrons, and you use these neutrons to probe the material.
How do we really measure it?
So what we measure typically are the angles. So for instance, in the experiment, the rocking curve experiment that I was showing you, you move your detector around to detect the Bragg peak. So you set it in the Bragg position, and then you rock the crystal around this Bragg position. Yeah.
So I was wondering what would happen instead of if I dope a larger spin as a defect than a non-magnetic.
Yeah, actually, I mean, I was thinking that I will cover that part. So because we have done such experiments where we have used cobalt, for instance, which is spin 3/2, but it has an effective spin 1/2. However, the spin by nature, because of the spin orbit, residual spin orbit coupling in cobalt, has a strong icing-like character, whereas the chain to begin with is Heisenberg-like. And so we have studied those things as well, and you get very interesting.
I know, yeah.
So can you relate that? So at these defects, can these spin-ons which are coming in, can they disappear?
So they are probably reflected back, so they form standing waves, and therefore you get this gapping in the excitation spectrum.
See, because I was wondering that this is non-magnetic, so let's say my two domain was being here. Can it not just flip? Because it does not have much energy to pay at that first dimension. So then in that case, kind of spin-on disappears.
So if the spin-on flips, then of course the net spin of the chain would change, right? And that cannot happen unless you pay energy cost.
Right. But at this defect size, maybe that's not too expensive.
So I haven't really looked at that.
How do you control the oxygen stoichiometry? Are you know, that can play havoc, right? Especially in the 1D.
It's a very good question. In fact, strontium 2, copper, oxygen 3, if you annihilate under very high pressures of oxygen, it becomes superconducting. So yes, oxygen is a control parameter. That's right. That's absolutely right. And oftentimes you don't have a very good control on the oxygen, but we have optimized the growth of these materials over the years, and we use TGA to.
It works with mirror. I think it won't work with anything else.
Yeah, cuprates are difficult to grow using flux method, and also with flux, there are other kind of problems that creep in. I mean, you know better than me that with float zone it's very neat. Yeah.
So while we're doping the sample, in that case, like the position of the dopants cannot be controlled.
Exactly.
So we can have like several different boxes.
Absolutely. So you will have a distribution of box size, right? So you have to model it. You have to take a Poisson distribution or something. That's why the gap is not hard. It's a soft gap. It doesn't disappear completely. I mean, at one point in one go.
So like even
You-
without changing the doping concentration, we could still like maybe see its effects. So because of this.
If you can change the distribution, but when you are doping your material, you don't have any control. So yeah, yeah. So if you're putting in zinc, you know that zinc cannot go to strontium or oxygen because they are very different. It will definitely go to copper side, but where exactly it will go, we don't know. Sometimes they may come two zinc atoms may come very close to each other. Sometimes they may be very far from one another. So on an average, if you increase the doping concentration, you will see the average effects. So on an average, the box size will decrease, and therefore the energy gap will increase.